Okay, let's get started. Everybody, can you see my screen? Hello, could you see my screen?
Yes, it looks great.
Yeah. Okay. So the midterm exam 3 information, you will take the exam 3 on November 11th. This means next week, Wednesday. Uh, then in terms of syllabus, you have to look class lecture 27 through 33. So today actually it is 32, and then on Monday it will be 33. So that's why I have included Monday's class as well. Uh, and then you have to look all numerical problems, homework, and the quiz that you did in last class. And in terms of book chapters, 16, 17, and 12. So currently I am on 12. 12 is three-phase system, three-phase circuit, and 16 was two-port network, and 17 was about that Fourier transform technique. And then as usual, you might expect 4 to 5 questions. Now, as I already told you before, that among 3 midterm exam, I will be picking up the best 2 for each of you. So that's why I recommend you all to give these exams so seriously as well. And then you are covering the whole syllabus, these 3 chapters, and then again there will be comprehensive final exam. I think I will remind you about that. I forgot the date, probably 1920 or 21, 22, something like that of this month, the final exam. That is different. That is, you all need to attend. And as I said, in the midterm exam, for example, you got 95, you got 90, and you got 80. So your 80 will be cancelled. So therefore, for everybody, whatever you get in 3 exams, your best 2 will be picked up. So then in that way, like you can learn well, and then also it will help you get the good grade. Okay, so again, I will remind you about this exam. You start looking from 27, so 33, just 3 chapters. Okay, so first of all, then how was your class quiz in last class? Were you all able to answer both questions?
Yes.
Okay, okay, so still, okay, so still I have not looked. So on Monday, I will discuss you the solutions of that. So just wait. Okay, so moving forward, you remember that we were discussing the three-phase system, three-phase circuit. And I think that on Monday, I showed you this slide at last. We were discussing the relationship between phase voltage and line-to-line voltage in case of both Y system and right side, the delta system. So as you can see, in case of the delta, if you see the voltage, like this is phase A, phase B, phase C, but the voltage between phase A and phase B, this means if you connect a voltmeter here, for this example, it will show you 480 volt reading. The same thing, if you connect a voltmeter just across this point and this point, this means across this coil, which we say the phase voltage. So because of this structure, in this case, the phase voltage and line to line voltage is the same in case of the delta. Then similarly, in case of the Y, again see, the phase current, the current that is flowing here, for example, from this point to this point, and if you add a ammeter here, then the same current will flow. So this means in case of the Y circuit, the phase current and line current is the same. So probably you remembered that last class I mentioned, if you measure the current just here, that is called the phase current, or you are measuring current through this coil, that is the phase current, phase current. Once you are measuring the current here, then that is called the line current. But for this structure, for the Y system, because that line and then coil is in series, so the same current will flow. So the conclusion is line current and phase current are the same. But everybody see the voltage. So voltage between phase A and phase B, that is called line to line voltage, or between phase B and C, line to line, or between C and A, that is line to line. So therefore see the relationship, and then this is the neutral line, as I mentioned in last class. For Y system, because this is the common point, and then at the common point, the neutral line is connected. So like you all know that at your home, you have one of these three phase and the neutral line. And the neutral line is finally connected to the grounding system for the safety purpose. So here everybody see, if you measure the voltage, for example, you are measuring voltage between phase A and then that neutral line. So it is giving you 120 volt. So this voltage you will call the phase voltage or phase to neutral voltage. But then see, if you measure the voltage between phase A and between phase B, look this one, it is 208 volt, which is root 3 times of this one. The same thing, any of the two phases, look, between phase B and phase C. This is called line to line voltage. So line to line voltage is root 3 times of the any of the phase to neutral voltage. The similarly here similarly here in case if you measure the current here, everybody say, if you measure the current at this line, and if you measure the current in any of the phases here, so line current will be root 3 times of the phase current. In this case, you see clearly, you understand that the current here and current in this coil will not be the same. So therefore that current will be root 3 times. So that's why in summary, what I am talking, by mouth. So for your convenience, I have prepared this one. So everybody see, that is the conclusion. For delta connection, the phase voltage and line voltage are identical. So this means this is called VLL, L dash L, line to line voltage equal to V phase, phi symbol. For Y connection, the phase currents and line currents are identical or the same. This means you can say IL equal to I phase. And now come back. For delta connection, the magnitude of the line current is root 3 times the magnitude of the phase current. The thing that I just told you for this case. The magnitude of line current, this is called line, is root 3 times of the phase current here. That is the meaning of this one. So IL is root 3 times of whatever the phase current is. Similarly, for Y connection, the magnitude of the line to line voltage is root 3 times the magnitude of the phase voltage. So therefore from today, everybody you will keep this thing in mind. Therefore, to solve numerical problem, to understand any circuit, so you must need to remember this thing. So therefore, it is easy to remember. In case of delta, voltage will be the same, phase voltage, line voltage. For Y connection, both current will be the same. Only the thing you have to remember this one, for delta connection, the current line current magnitude will be root 3 times of the phase current. And in case of Y, line to line voltage will be root 3 times the magnitude of the phase voltage. Okay, so soon I will solve some numerical problems for you. Then we will be utilizing this concept. Then it will be clear to you. Hold at this moment. Okay, now moving forward. What I said, what I am telling here, everybody see, the sum of the line voltage is 0 for a balanced three-phase system. So this means VA plus VB plus VC is 0. And similarly, IA plus IB plus IC 0. So probably you remember that in last class, I mentioned that three-phase system can be two types. One is called balanced or symmetrical, and the other one is unbalanced or unsymmetrical. So balanced mean they have the same magnitude for all three phases. For example, VA has 100 volt, VB has 100 volt, VC has 100 volt, and they are properly maintaining 120-degree phase difference. Probably you can remember that I was telling you that each phase are displaced by 120-degree. Distance between A phase to B phase 120. So this means, as I said, that VA plus VB plus VC should be 0 in case of balanced system. But if it is unbalanced system, then it will not be 0. That is the thing. That is the conclusion. So therefore, I mean, you can prove this one. Then for example, you take any example. You assume your VA is 100 volt and you 100 volt, and then add the phase angle. VA phase angle is 0. VB phase angle is minus 120 degree and VC phase angle is plus 120 degree. And then you just add those three by using phasor algebra, you should be getting 0. So that's why if you see any balanced system and you need to add all those three voltage or current, the straightforward you can write 0. But keep in mind, if it is unbalanced system, then you will not get 0. For example, your VA is 100 volt, but VB is 90 volt or 110 volt. If there is any change either in magnitude or phase angle, then you should not get 0. There will be some number. That is the unbalanced system. So therefore everybody say, because I said IF plus IB plus I say 0, therefore the neutral conductor does not carry any current. Probably you already know this thing from your basic knowledge. The neutral conductor does not carry any current. That is IN 0 if the source and load are both balanced. This means that, then come back this example. For example, at your home, you have phase A and then you have the neutral line. Therefore, neutral line actually does not carry current. So therefore, you see that this is the three-phase system. For example, this is A phase, this is B phase, and this is C phase. If the system is balanced, for example, in this case, all on 20 volt, and they have the 120-degree phase difference, and if you sum, then there should not be any current flowing through the neutral. Now, if it is unbalanced, keep in mind, if it is unbalanced, then there should be current flow through the neutral. And that neutral current will flow through your grounding system. For example, your home has grounding system, or your company has grounding system, or a building has grounding system. For some reason, system is unbalanced and some current is flowing through the neutral. So therefore, the problem is that this neutral line has some capability, because if current flows through the neutral, then this coil will be heated up. And if the current is too much, and if current flows for a long time, then this neutral can be burnt out, disconnected, or damaged. So this means that you are unsafe. You don't have the neutral line, and because neutral line got heated and burnt off, so that has been disconnected with the with the grounding system. So you are fully unsafe. So that is one thing. The other thing is that, for example, the neutral current is flowing because of unbalance and it is going through the grounding, and you are standing nearby the grounding and you are barefooted. You don't have socks or you don't have any shoe. For example, you might get shock. If that place, if the grounding place in the soil is like kind of wet, or it's a rainy day and current is flowing, so you might get shock. That is dangerous. And it depends on how much current is flowing. You might get severe shock if you are barefooted. So that's why unbalanced system is not desired. Always it is preferred that system should be balanced. So, everybody, could you follow me what I am saying?
Yes, sir.
Yes.
Yeah. I think that makes sense. That is the necessity of having the neutral line. Like every house, every load has the neutral line. And finally, every equipment is grounded for the safety purpose. So that in case there is current, that goes through the neutral line. Yeah. So therefore, as I said, And not only the problem of that you're getting shock or it is getting burnt up, in real practice, another thing happens. For example, this is your system, this is your home, just an example, and you have some unbalanced and current is flowing and it is going to ground. Right side, you have your neighbor, for example, another house. That house has the grounding. That house has no problem. Their system is fine. But because they are grounding and your grounding is nearby, and if there is good connection through the soil and it's a rainy day or it is wet, then from your grounding system, the current will enter into their grounding system and they will be affected. It also happens in real practice. It might happen. So this means issue is at your home, but that is causing the problem your neighbor through the grounding. That is one thing. The other problem can be, this is the neutral line. You might have noticed outside the overhead line, the telecommunication line or the telephone line, they carry the same neutral line, the telephone line. So therefore, for example, your system is unbalanced and current is flowing. The same current is flowing through the neutral of the telecommunication line. Now the problem is that, for example, you are talking through phone to someone long distance or the overseas international call. Sometimes you might see the interference or too much noise on the line, or the at all you are not making the calls because of that interference through the neutral line. Because the in the overhead lines, power lines and the telephone line, they share the same neutral line just to save the conductor cost. That is other problem. So therefore, in summary, in any case, the unbalanced system is not desired. Okay, so now moving forward. So yes, that is the thing I mentioned here. That typically the neutral conductor does not carry any current, but for an unbalanced system, current flows through the neutral. Now, the other important thing, current flows through the neutral. This is true for the Y connection. I mean, this conclusion goes for left side configuration. How about the right side? Is there any neutral line here? No, there is no neutral line here. So then what happens if the voltage is unbalanced? So here, because there is no neutral line, what will happen? For example, voltage in this coil and in this coil is not same. So consequently, there will be current because their sum will not be zero, as I concluded. Their sum will not be zero. Also, their sum will not be zero. That additional current will be trapped, will be blocked by these coils. So gradually, these coils will be heated up and they may burn. That is the problem for the delta system. And in this case, it is not going, it is not affecting the neighbor because there is no neutral line. That is okay. That part is fine as compared to this case. But the coil itself might be damaged if it is the unbalanced and that unbalanced goes too long. So therefore, in both cases, there is problem. So this is more severe because current will start flowing through the neutral and go to the grounding. But this case is also dangerous. Okay, so now moving forward, here you see there is a like summary slide. This slide is very important. Like everybody as a engineer, so you must remember this one. Like if this slide is in front of you, right, then you can solve any problem about the three-phase system. So therefore, see what I have written for you. For delta connected system, I am just summarizing now. Line voltage, sometimes the simple just VL is used. If you remember that here I was telling you the line voltage, everybody see the line voltage VLL. So sometimes simply VL is used, symbol. So VL means VLL. So just keep in mind. So that's why here I have written simply VL. VL means line to line voltage. So line voltage means you will keep in mind line to line voltage. Because you see, voltage cannot be only with one lines. For voltage, you need 2 points, either line to line, I mean one phase to other phase, or phase to ground, phase to neutral. So that's why when I'm saying line voltage, this does not mean that only one phase. Because if you have voltmeter, you must need to connect between 2 points. Therefore, everybody keep in mind, line voltage means line to line voltage, simply VL equal to phase voltage, VP. Sometimes in the book or literature, symbol phi is used. I mean, here I'm showing you that phi symbol, but instead of this one, simply phi symbol is used. And it is easy to remember. Phase voltage VP, line voltage or line to line voltage VL. And for delta connected system, line current IL is root 3 times the phase current IP. Then same thing, same conclusion for Y connected system, line current IL equal to phase current IP. And line voltage is root 3 times of phase voltage. And then now come back. This is the voltage current relationship. What about the power? So everybody see what I have written first. Total three phase real power. You remember the real power and reactive power that we have learned in case of single phase system. So what formula we used? We used like VI cos theta, right? And we used VI sin theta to represent reactive power. But today what I am writing, total three phase real power. So this means everybody look, without 3, that Vp Ip cosine theta, this equation goes for the single phase system for any of the phase. For example, phase A or phase B or phase C. And then I am multiplying by 3. I am assuming that that is the balanced system. So keep in mind that this equation is for balanced system. My assumption is that in all three phases, they have the same voltage magnitude, they have the same current magnitude, and they have the properly phase difference of 120 degree. Then you can straightforward multiply it by 3. Now, everybody say, if it is unbalanced system, then you cannot multiply by 3. So what you have to do? You have to do one phase at a time. For example, when you are doing for phase A, so VA IA cos theta plus VB IB cos theta plus VC IC cos theta. You have to do 3 times for 3 phase and then you sum up. Because that is the unbalanced system. You cannot say that that is the 3 times. Because A phase power can be, for example, 200 watt, B phase power can be 300 watt, C phase power can be 90 watt. You don't know. Because the unbalanced, how much unbalanced, what is the magnitude difference and phase difference, you don't know. So you have to do one phase at a time and then you need to sum up. In case of total 3 phase real power for unbalanced system. But for balanced system, straightforward 3 Vp Ip cos theta. Everybody, could you follow me so far what I am talking?
Yes.
Okay. Then after that, everybody now listen very carefully. Then this is much more important than what I said up to now. Very carefully. Can you see the next equation? What I have written, real power P root 3 VLIL cosine theta. And then in parentheses, I have written delta or Y system. This means this equation is applicable either delta or Y for both system. And I have written reactive power Q root 3 VL sine theta. Now, can you see the symbol here and symbol here? Here it is VPIP. What was VPIP? VP was phase voltage. I said above VP phase voltage, or here V phase voltage. What was IP? IP was the phase current, like phase current or phase current. But what symbol I am using here? VLIL. What is VL? Line to line voltage. What is IL? Line to line current. Sorry, line current. So, and then that times, can you see? It is root 3. Instead of 3, it is root 3. So this means that the difference between those two equations in real practice, for example, you purchase a motor, three-phase motor, for example, or you purchase whatever the device, three-phase device, and you are looking the specification or the ratings of voltage, current, power. Voltage and current are always expressed in terms of the line quantity, like line to line or the line current. Hardly it is mentioned the phase quantity. So that's why, because in real practice, everything goes in terms of the line to line or the line current. That's why instead of using this equation, it is convenient or preferred to use this equation. So now the question is, everybody see pretty interesting. Instead of 3, how it is coming root 3? That is the magic number. You see, and that gets difficult because here it is 3, it is root 3. So the reason is that now everybody see this example. This is your basic equation. From here, you can derive this equation. Now, everybody look what I have written here. For delta connected system, what is the voltage relationship? VL equal to VP. Everybody follow me properly. VL equal to VP. Look this equation. You replace VP by VL. You did that. That I am doing here. I replaced VP by VL. And replace IP by IL. So for the delta connected system, what is the relationship? See this on everybody. IL is root 3 times of IP. This means if you replace IP, it will be IL over root 3. See this one. That I am putting here. IL over root 3. And then what you are getting? This root 3 here, and then root 3 will come here because this is 3. So what you will be getting? Root 3 VL IL cosine theta. That is the thing I have written here. Then now come back the Y connected system. If it is Y connected system, again you replace these two quantity VPIP expressed in terms of line quantity for Y connected system. What is the relationship for Y connected system? IL equal to IP. You replace IP by IL. I did that one. How you can replace VP? You look. VP is that VL over root 3. So I replace this one, this VP by VL over root 3. Again, you see root 3, here root 3. So root 3 VL IL cos theta. Same equation. So that's why I have written here, whether it is delta or Y, it does not matter. For both system, real power will be root 3 VL IL cos theta. Therefore, from right now, everybody just memorize this one. That real power for 3 phase root 3 VL IL cos theta. Never ever don't write just the 3. It is not 3 VL IL cos theta. If you want to use 3, then you have to use VP IP cos theta. And if you use VL IL symbol, then please use root 3. Don't say the 3 it is. And as I said, both equation is the meaning is the same, but in real world practice, always voltage and current expressed in terms of the line quantity. That's why you have to use this one. Then similarly, reactive power, you all know, reactive power Q is 3 VPIP sine theta for total 3-phase power. But then accordingly using these, relationship, root 3 VLIL sine theta. And the same thing goes for whether it is delta or Y system. So therefore, see, these are the difference between single phase and 3-phase. In case of single phase, you all learn real powers VI cos theta. And you did not even take care whether it is line or whether it is phase, because it was single phase only. So it does not matter what symbol you use, whether you use P or you use phase, because it is only one phase. It does not matter. So that's why you all use just VI cos theta. Of course, VI, those were the RMS quantity. In this case also, this VLIL, those are the RMS value, effective value, not the peak or the amplitude. Then similarly, I think you remember this thing, power triangle, probably you can remember that phi, then y-axis q, and then this is hypotenuse S, apparent power. So in this case, you see apparent power is root over phi square plus q square. And then cos square theta plus sin square theta, it will be 1. So ultimately you will be getting root 3 VLIL. So everybody remember, apparent power is for three-phase system, root 3 VLIL. But you remember, in case of single phase, it was just VI. VI, the unit was volt ampere. And then this is the power factor, power factor was cosine theta. So phi over S. Can you remember that power triangle, what I am talking about here? So just for a minute.
Yes.
Right.
Yeah.
The apparent and real.
Yeah. Just hold on for a second. I am mentioning this thing. Yes, everybody remember this triangle. Like this is your theta, and here it is phi, the real part. Here it is that reactive part, and this one is your apparent part, which is root over phi square plus q square. Okay, and then that cosine theta. If you take the cosine of this angle theta, so cosine theta is p over s. That base over hypotenuse. Yes, that is the thing I was telling. And then you notice what was that real. So the real power was root 3 that VL, IL and cosine theta. That was the real power expression for three-phase system. And this one was that one, that root 3 VL sine theta. You will be using this one. And then S, like if you make root over p square plus q square, this, then ultimately you will be getting S is root 3 VLIL. Yes. Not 3 VLIL. Always you remember this number, root 3, that root 3 and then root 3. That root 3 is coming. So now you need to use this concept to solve the problem and all the things that we discussed so far. Everybody, could you follow me?
Yes.
Yes.
Okay, great. Yeah. So just everybody note down these things. What I would recommend you, like I'm taking you there again. You just take this on. Everybody, I already uploaded, this slide. What I recommend you all need to take a print of this page or take a photo in your cell phone. And unless you can memorize everything, you keep this thing in front of you. So then that will be much more easier and easier to solve any problem, to understand anything. Then you can see what is the relationship, what is the interaction, easily you can understand. Okay, now I will take you to a numerical problem. Then I will go back and forth and I will show you, then it will be helpful for you. Everybody read some practice problem. Example 1. Assume that the phase voltage of a Y-connected source at its terminals are given as Vn is this number, Vbn is this one, and Vcn is this one. Then determine the following line voltages of VAB, VBC, VCN. And next part, if a balanced Y-connected three-phase load of Gn equal to Gbn equal to Gcn 1030 degree ohm is connected to the source, then find all the phase and line currents. So therefore, everybody see, because this is Y-connected system, you see clearly it is Y-connected source. That's why you can say voltage are given between phase and neutral. That we discussed, the Y system will have neutral. So that's why Vn means a phase to neutral voltage. This means this is not line to line voltage. And then can you see the phase difference? This is 0 degree. Then Vbn, it should be minus 120 degree. But then if you go anti-clockwise, plus 240 degree. And then C phase, it should be minus 240 degree, but if you go anti-clockwise, that is 120 degree. So this is given. And everybody say, it is balanced system because look the magnitude, 277.13, 277.13, here the same. Magnitude same. Also you look the phase angle from here to here. If you go clockwise, the difference is 120 degree. Or even if you go anti-clockwise, difference is 120 degree. And then here you see, again, that is anti-clockwise 120 degree. And each phase are the properly 120 degree. Between this phase and this phase, 120 degree. Between this one and this one, 120 degree. So this is the example of balance system. Now, based on that, you calculate line voltage. Line voltage means what is the voltage between phase A and B? That is the meaning VAB. What is the voltage between phase B and C? That is the meaning. What is the voltage between C and A? So therefore, first let's solve this thing, and then I will come back again for the second part. So therefore, everybody say, let me make it bigger. Okay, everybody see. Look, first I am drawing a picture because the problem says it is the Y connected. So that's why first I drew a Y connection, and I'm designating A. This is B, and then this is C. Like 120 degree, 120 degree apart. And everybody look, the common point I have designated N. N means that is the neutral. And here I have labeled VAB. This means when you are measuring the voltage across these coils or this coils or this coil, it is VAN or VBN, VCN. Those values are given. Those values are given here, VN, VBN, and VCN. So that I wrote down here. So what are that on V1? V1 is this one, or this one, or this one. And now I have labeled, you see, between this point and this point, meaning that is my VAB. This one is VCA. So between here and here it is between BBC. That is the question. The first part is that one. Determine VAB, VBC, and VCA. That you have to find out. So therefore, everybody look how I am solving what I wrote, VAB. Keep in mind that because when you are adding the AC quantity, because it is the phasor, these things are given in phasor, and phasor means vector. So therefore, you have to properly follow the direction as well. That is the definition of the phasor or vector, means it has a magnitude and it has a particular direction. This means phase angle in this case. So therefore, what I am emphasizing, look my equation VAB, what I am writing, VAN plus VNB. Because I am going from point A to B, so I am fully following this direction, VAN plus VNB. Now here you look, what is given? It is given VAN, next it is given VBN, then it is given VCN. VN given in this direction, then that is the magnitude at phase angle. But here you see, I have written VNB. So VNB is not given here. VBN is given. That for vector or phasor, these notations are important. Direction, is it NB or it is VN? These things are given. I cannot change these things because these were given in the problem. So I cannot. But here, I wrote VNB. So that's why, you see, and now I am changing the direction. That's why I put a minus sign. And I am writing VBN. So everybody say it was written VNB, but I am changing the direction. I am going in this way, opposite direction. So I put minus. Why I did that? Because VBN was given, not NB. That's why I put this on. And then now I can substitute the values. VN value, the first one. And what is VBN value? This one. And then if you have calculator right now, and if you this minus, then what you get? if you right now everybody use your calculator, you should be getting this one, approximately 480, and angle should be 30 degree. Can you check this one, everybody, in your calculator? Right now you do that.
Yes, they are all good.
Okay, both are the same.
Yes, they all match up.
Okay, great. Now everybody do one thing. Can you multiply this number by √3 to 77.13 multiplied by √3? Can you just do that?
It was 480.
Yes, 480. You see, that is the thing we learned. So therefore, it justifies. Or what I learned, everybody look what I'm saying. It is Y connected system, right? This is Y connected system. Vn, this magnitude, I mean, forget about the angle. Magnitude was this one for each phase to neutral, phase to neutral. What you are finding now? You are finding VAB or you are finding VBC and, oh, sorry, here I wrote the symbol wrong. It should be VBC, it should be VCI. I'm really sorry. I'll be connecting the symbol. Again, I will re-upload this slide. It should be VC and it should be VCN. Anyway, so you are measuring line to line voltage. What was my conclusion? Look, everybody, what was my conclusion for Y connected system? What is the relationship? Line to line voltage should be √3 times of the phase voltage. That is the thing I learned. And now that justifies. You see, I found VAB, which is 480. And then this is the phase voltage. If you multiply this magnitude by √3, it is giving you 480. So then this is right. It is justified. Sorry, this one for Y connected system. Could you follow me what I'm saying?
Yes.
Yes. Yes. Now, the same thing, as I said, first of all, everybody, I mean, after the class, I am going to change this slide. I mean, currently I already uploaded, but I wrote the wrong thing. It should be VC. It should be VCA because, you know, VB and CN are given here. So I made mistake, VC and VC. So now everybody see what would be similarly, you have to do these two calculation. What would be VBC? Everybody look this one. What would be the equation for VC? VBN plus VNC. See, I am going from B to C. So similar to this, it will be VBN plus VNC. I mean, when you will be doing, I just wrote similarly VBCA. I just wrote the answer, but you can, right now you can test. It will be VBN plus NC. But then BN value is given. This is as it is, but CN is given. But I said VNC. So you have to change the sign likewise that you will be writing VBC is VBN minus VCN because it is in this direction. Then use this number. This means if you subtract this one from this one, then you should be getting this result. Right now you can test. Or if you are doing VCA, look this one. So VCN plus VNC, or in other words, sorry, VCN plus VNA, or in other words, VCN minus VN. This means if you subtract this one from this one, you should be getting this one. Therefore, you see, in all cases, you are getting 480, 480, because that should be the √3 times. Everybody, could you follow me so far?
Yes.
Yeah, okay, great. So as I said, I mean, don't be confused. You see, this is VC and this is VCI. I just wrote the wrong notation. I will change this. Okay, now there was the B part. Now everybody see what was the B part. Oh, let me a little bit zoom in. So you see the B part was if a balanced Y connected three-phase load of Zn equal to Zbn equal to Gcn, which is 10 at an angle of 30 degree ohm, is connected to the source, then find all the phase and line currents. So this means in first part, it was only the source, Y connected source. That is the power source. But then with this power source, Y connected three-phase load is connected. And in all three phases, you see, GN, GBN, GSN, all three phases have the same magnitude of the impedance. So under that condition, find out all the phase and line current. So that's why for the C part, everybody see what I am doing here. So I have this one at first, this source. So that's I am drawing here. And this is the neutral point. And right side, I am representing that again Y connected load. So this means you look, I am connecting A to A prime. Here I have given the name like A prime, B prime, C prime. I mean, basically the A phase, B phase, C phase, same thing. So just to understand that right side is load and left side is the source. So I am connecting, you look, A to A prime, C to C prime, and then B to B prime. And this is the neutral. So the right side load is also have the neutral because Y connection. Consequently, I am connecting this one. This means what is happening? I mean, for example, this is power source, this is load. You look my direction of the aisle, line current is entering into going into this coil and it is coming at this point. Same thing happening for here. It is going, coming here. For C phase, it is going, coming here. And all three are then going through this one. So I mean, that is the flow. In that way, the circuit is working. That is the meaning. So therefore, everybody see, your question was find out all the phase and line currents. This means how much current is flowing through these coils and what is the line current. That is the question. So therefore, everybody say, because this is Y connection, the current that is flowing here, which is called line, the same current is entering to the phase because it is connected in series, right? Yeah. So that the current that is flowing here, the same current is entering here. So this means if you know what is my, for example, for look for this one, how much current is flowing, you look that the impedance are given. GN is 1030, GBN is this, GCN is this, which was given here. This one, GN equal to GBN, GCN, which was 10 at an angle of 30 degree. That was given, that I have placed here. So everybody look, if you just know what is my voltage here, what is the voltage between A prime and then this neutral, and if you divide by the respective impedance, that will be your current here. And that will be the current here as a line current. So that's why what I have written, ILA is equal to IPA, meaning that the line current for phase A and line current for phase A, phase current for A, that is the same thing, which is VN over GN. Now, because you know that this is A prime and this is the same thing, so I already know what is the voltage VN. The same voltage is here at this point, VA prime, and those voltages were given. Look, VN, this VBN, VCN, already those were given. So what I am doing, I am just plugging those values and my GN value is this one, 1030 degree. So I got this number, 27.713 angle minus 30 degree ampere. And then similarly, I am doing for phase B, for phase C. So that is the answer. I mean, here it says, find out all the phase and line currents, but the phase and lines current are the same because this is Y connected system. And that we have learned. Look, for the Y connected system, line current equal to phase current. So that I got here. Everybody, could you follow?
Yes.
Okay, so therefore once again, like after the class, again you need little bit practice. You take pen and paper, draw these circuits and do this thing, take your calculator, and then it will be clear. These are, I mean, not difficult, but because very first time you are looking the three-phase system, that's why it may look like little complicated, but not complicated at all. Just you need to understand. If you understand, then like it's fine. Okay. Then I will show you another example and then I will continue on Monday as well. Okay, example 2, everybody read. A balanced delta connected three-phase load withdraws 200 ampere per phase with a leading power factor of 0.85 from a 12.47 kV line. Then determine the following. Find out the line current of the load, the phase voltage of the load, the three-phase afferent power, the three-phase real power, the three-phase reactive power, and three-phase complex power. Like all type of power are being asked. Three-phase real, reactive, complex, and afferent power. This means exactly these things. We have to find out all of these things. That is the meaning of this one. So therefore, the first thing is you have to do, you draw a delta connected three-phase load. That is the very first thing. For this type of problem, always please draw a simple circuit for your own understanding. And then see what things are given and what things you have to find out. Then you can figure it out. Therefore, very first step, everybody look, I am drawing a delta connected load. See my solution. First, I am drawing a delta connected load. Look the structure. And you see, the problem says the phase current is 200 ampere. This one. Look, withdraws 200 ampere per phase. And with the leading power factor from a 12.47 kV line. This line means this is line to line voltage. This does not mean that this is line to neutral or the phase voltage. Clearly it says this is the line. Line means line to line voltage. So that's why what I am doing, everybody see here, VL 12.47 kV. And what I am indicating, line to line between this line and this line. And I have written that power factor value, this one, which is cos theta. And from there I calculated sine theta. Like cos theta is this, then theta is cos inverse, and then find out sine theta. I just did that. I will be utilizing this sine theta later. That's why I did. Now, everybody see, what was the first question? First question is find out the line current. So meaning that this current is given, this or this on this is the 200, 200. What is the current here? How much current was coming from the line and that entering the load at this point, or at this point, or at this point. So line current means you have to find out current entering here, or here, or here. So then what is the relationship? What we learned? We learned in case of the delta connected system, see everybody this one. Line current is √3 times of head current. That is the reason I am telling you that everybody after the class, please you take a printout or just this slide where all the equations are written, or either you remember or take a photo in your cell phone. Unless you can memorize everything, you take it. Yes. Like I am habituated over the years I am doing, so I know all of this. Easily I can remember. For you, at first you look and do, and then over the time you will be fine. So what I am doing, I utilize that concept to find out line current. What I did, √3 times of 200, straightforward. And then I got this result, 173.1 ampere. And then what I am doing here, you see, in box, I am writing IL is this magnitude. I need to put an angle. How I got 31.78 degree? Everybody look, cos theta is this one. So if it is cos theta, what is the corresponding theta? That theta will be 31.78 degree. And what the problem said? Leading power factor. Because it is leading power factor, so I am using the angle plus here, positive. If the problem said with a lagging power factor, if it would be lagging here mentioned, then you would be using the minus sign here. The angle that you will be getting from cos theta power factor, if it says lagging, you will be putting minus sign here. In this case, because it is leading, so that's why I am putting the plus sign here. Okay, that is fine. The question number B was find out the phase voltage of the load. Phase voltage. So now see this one. What is my line to line voltage? 12.47 kV. What is the phase voltage? It is the same because this is delta connected system. This voltage and voltage here is the same. This voltage or voltage here is the same. Or this voltage or voltage, this point and this point is the same. And that is the thing I have learned for delta connected system. Line voltage VL is phase voltage VP. So that's why I am directly writing phase voltage is 12.47 kV. Straightforward, that is the answer. Because this is line voltage and I am also measuring across this one. Everybody, could you follow me?
Yeah, this is making sense.
Yes, yes. Just as I said that you will be taking, and this is very important, this slide and this all those previous talks. I mean, these things you keep in mind in front of you, look, and then it will be clear to you. I understand that very first time you are looking these things, it may look little bit complicated, but not complicated at all. Just it's a matter of your proper understanding. So therefore, you all need to understand. And as I said, especially for the those whose major is computer, so in our curriculum, we don't have any course that will be taught again you the three-phase system, unless you yourself you learn the things. So therefore, this is your last chance to learn these things, three-phase system. Then those whose major is electrical, then again you have the enough chance in the energy conversion class 4201 that you must need to take that on. That is required course. Again, this will be the first chapter there. And like I spent at least 5-6 classes on that three-phase system. There are a lot of talks. But for computer major, you please learn as much as possible from here. Then, I mean, whole life in your engineering life, this is enough, this understanding. Okay, so then as you can see, I think we don't have much time and some of you have next class. You just look, the next question is, what was the three-phase apparent power? What was the three-phase real power? What was the three-phase reactive power? What was the three-phase complex power? So just I am giving you the pointer and then you will look. What I have written, three-phase real power, √3 VLIL cos theta. See the symbol, √3 VLIL cos theta. And then this is √3. What is my VL? This one is my VL. What is my IL? This is my IL that I calculated. This one, this magnitude, IL. And what is my cos theta? This is my cos theta power factor that I am putting. And then I got this result megawatt. Similarly, what is three-phase reactive power? √3 VLIL sin theta. And then again, this magnitude is the same that I discussed here. Sin theta is this one. That is the reason I calculated sin theta from this one. And then this is megavar. Look the unit, megawatt, this is megavar. You might express in kilowatt if you like, or kilowatt, that is fine. But it is convenient because it is you can express with simple number if you use megawatt. And then this one, the last one, three-phase complex power. Three-phase complex power. What is the complex power? Can you remember in single-phase system? VI conjugate. VI conjugate, if you can properly remember, because I think it has been more than a month ago, we discussed that thing. VI conjugate. Therefore, accordingly here, √3 VL IL conjugate. IL will be complex conjugate to calculate complex power. So look, this √3, this is VL. IL conjugate, look, what was my IL magnitude? That is the reason I put it in box. This angle is plus here. But once I am doing IL conjugate, sign is changed. It is -30 on here. And then if you multiply this one, I got this one. This is in MVA, megavolt ampere, the unit of complex power. And then after that, what I am doing, just in 30 seconds, I will release you. I converted from here polar form to rectangular form. And then I got this result, this minus this. So first part represents the real power and the second part represents the reactive power. And then really you see it matches. what I calculated in part C, 3 point on it, 3 point on it, or 1.9 it. I got 1.9 it. I got the minus sign. Minus sign indicate that that is the capacitive reactive power. That can provide the leading power factor. That's why it was the leading power factor. If it would be the lagging power factor, then for sure you would be getting the plus sign here, because it would be the plus sign here. It would be the minus sign here. So therefore, I mean, you are done until this. You don't need to do this thing, or you can do. I am doing this thing and I have shown in box just to verify, just to prove that, okay, I did correctly in part C and in part D. I am getting the same thing. Because you know that complex power consists of real power and reactive power. Okay, I think, please, those who have classes, you please leave. So everybody, could you follow me so far?
Yeah.
Okay, so please everybody take your time and you try to understand at home, and then I'll be continuing on Monday, and then it will be much more pretty much clear to you. Yeah, and I will solve another 2 or 3 practice problem for the 3 phase, and then you all will be ready for the midterm exam 3. Okay, so does anybody have any question, comments, anything? So if no, then I am stop sharing at this point.